Section 17.2, Stokes theorem. And so Stokes theorem is what is an equivalent to Green's theorem in three-dimensional space. So Green's theorem basically worked in two-dimensional space and it was flat. Now Stokes theorem is going to work in three-dimensional space and surfaces can be non-flat. First, as we did for Green's theorem, we did the orientation of the curves. And here we want to discuss the orientation of the curves, and this time it are surfaces and how does the surface relate to the curve and so on and so forth. Then we define the, then we go through the theorem itself, explaining what the theorem is. Then we do a couple of examples. So let S be an oriented surface with unit normal vector n. Recall that boundary, that's the partial S is boundary of S, consists of a set of closed curves. Now, we can orient the boundary S as follow. If you're walking along the boundary of S with your head to the direction of the normal vector, see this person, the head is in the direction of the normal vector, and you stick your left hand out, then your left hand should point to the surface itself. The other one, and the other way to orient the boundary is using the right hand rule. And that's if you're putting your basically thumb in the direction of the normal vector, and you moving your hand toward the direction on the boundary, then your other fingers should be pointing to the to the surface itself, and this is called a right hand rule orientation. There's a little video on the orientation that explain this better and comes after this video basically. So question 1, I click a question A of 17.2. Suppose that pad surface shown to the right is oriented outward, oriented with outward normals. Which of the boundary components C1, C2, and C3 is oriented with right hand rule? Now I'm thinking about walking along any of these paths, and if my head is basically sticking out of the page, and if I stick my left hand, it's going to left arm, it's going to be outside. If I'm walking on this pad and I stick my left hand out, my left hand would point to the inside. For this one, if I stick my left hand, it would be inside again. And if we are having the normal, stick out this way. And so with a normal outward, C3 and C1 are the basically the correct orientation, the right hand rule orientation. So C1 and C1 and C3. D is the answer. So what's the Stokes theorem? Let S be an oriented surface with smooth, simple, closed boundary curves, and let F be a vector field whose components have continuous partial derivatives. Then the contour vector line integral over the boundary of S of F dr is going to be equal to double integral of curl of S ds. That's the surface integral of curl of F, the vector surface integral of curl of F over the surface, where the components of boundary of S are oriented using the right hand rule orientation. So for this to be true, the direction of the boundary should be following the right-hand rule orientation, or otherwise one is going to be the negative of the other. Now, Green's theorem, fun fact, Green's theorem is a special case of Stokes' theorem. If D is a region in the plane and boundary of D is given a right-hand rule orientation with n being equal to k, that's the unit vector in direction z, then Stokes' theorem becomes the contour integral of over boundary of D of FDR, contour line integral of vector line integral of boundary of over boundary of D of FDR, and it's going to be okay equal to the double integral of curl of F dot K dA, which is exactly Green's theorem.